We are ready to rock and roll, and I'm going to pass them over to you.
All right. So hello, everyone. This is my second time giving this presentation, and I've had a lot of caffeine, so I'm going to try to still slow down and get through the whole thing. But my name is Chet Wiltshire, and I am a graduate of the Math and Science Academy in the class of 2018. And I'm speaking today to, it sounds like the second half of the juniors in the STEM program, head of the Capstone project. So I want to give you some background on myself. I grew up my whole life essentially in Virginia Beach, and only recently moved to the Huntsville area after my first year of college. I was a graduate of the Ocean Lakes Math and Science Academy, and now I study aerospace engineering at the University of Alabama. I'm currently a senior, expecting to graduate this May. And in terms of looking back 4 years later on some of the classes that I used the most often and also enjoyed in high school, I really did enjoy physics, the computer-aided design classes, and also leadership-focused classes like public speaking. In terms of sports, I also was very passionate about soccer and swimming. So I did those 4 years at high school. I was a member of the OLHS pod squad, and I really enjoyed helping people in my free time while I was at high school and getting experience with meeting, teachers that I wouldn't have otherwise gotten to talk to. I specifically completed a senior capstone project pertaining to drones and flight controller configuration. And that's also what I kind of did for my fourth quarter integrated STEM project. And just, trying to be funny here, but sometimes I was known for the person that would doze off in class a bit. So in terms of what my STEM project looked like, I'm going to turn down the audio. It's a little loud in this, but one of the things I did when I was a junior, around that time in high school, I had a friend who was very interested in drones and actually learned how to build his own drone. He taught me how to do it, and I took that same drone that I built just to fly around and mess with, and for my STEM project, I tried to demonstrate a drone delivery concept where I modified it to carry a small payload of quarters to basically from one point to another, drop it off with a servo, and then release it and come back. So that was a demonstration of my STEM project. But in terms of the senior capstone project, it's kind of all encompassing in that I used that drone to study, without all the math necessarily behind it, well understood, the effects of changing the settings in the flight controller for the stabilization and control of the drone. And aside from that, I also got to work with my mentors to learn about flying drones commercially, how to take pictures and videos for clients in the event that that's something I want to pursue. And one of the cool things I'm trying to let you guys know from my experience is that not only did I get to go to the science fair, but I also was able to present at an awards banquet for the AFCEA. I got third place for them at the science fair, and they invited me to their banquet. And then I also got a scholarship from the American Helicopter Society as well. So in terms of your capstone project, the work you do can get recognized in the community. And for me, I was lucky enough that it could also contribute to going to college. So I want to show you guys a little more in depth of what it was like. So I found this picture of me talking to the students from not only my grade, but the academy about my project. So this was in the smaller auditorium, but not too different. Just 4 years ago, I know obviously things have changed, but essentially, I know you guys are nervous sometimes about presenting, and just want to show off what it was like for me back in the day. And in terms of the actual cool data, what I was gathering, I'm turning down the audio a little bit here, but for the drone, I mentioned I was trying to tune the flight controller. So I would change some settings in terms of the coefficients that control the three axes of rotation. So the roll axis, the pitch axis, and the yaw axis. And I would keep changing them up and down in terms of how much the effect they would have in terms of response time. And this example of the roll axis being oscillatory way more than it should be but the other two axes, the yaw and pitch, being stable. So you can see I was literally just in the cafeteria with the drone that I built with my friend, with a Bluetooth receiver on it, trying to record data from the gyroscope, accelerometer, and just trying to see like how it responds to giving it different inputs without necessarily understanding all the math behind how you would tune it. Oh my God. So you can still see like the oscillations here. This is this one's a gyro, so you can really see that's the roll axis going up and down the most. But yeah.
What? And that makes sense. Pitch and roll are.
You can hear my friend Nick West in the background talking about some of the stuff that we learned. So that was the exciting experience I did with just specifically the Capstone and Integrated STEM project, and pivoting towards like that, you know, how that gave me future opportunities. The same person that was my mentor for my senior Capstone project, Mark Crunchy Burgess, he also, you know, mentioned after my freshman year of college that they're looking for an intern at their company called Prevailance Aerospace, which is a small company that provides upset prevention and recovery training to pilots. I try to emphasize how important this is to people every day in terms of when you go on airplanes. You know, if you're flying to and from, you know, a hub, or you're going on a, you know, a venture ride, or you know, whatever. Maybe you're receiving a package from Amazon or UPS. They're flying your cargo. Upsets are very hard to recover from in the adequate amount of time when the autopilot does turn off, or when you do get into an unusual attitude. It's really important that people are well trained to recover in the safest and fastest way possible. So I got to work with my mentor after my Capstone project, and specifically for this, I got to fly with them and train clients, ranging from students that had just completed their first year, or I guess not first year, like their first solo, up to people that are corporate pilots and, you know, veterans. Some of them are even Navy SEALs, and really just learning a lot from the different people I talked to, and really obviously also the attention to detail when you're flying planes and doing crazy things like spins and flips. It really is important that you are detail oriented. So I want to show you guys just something pretty cool, demonstration of a spin recovery. So in a spin upset and recovery, there's a few things you do, but I think my mentor in the back can do a good demonstration of that. So I'm gonna turn the audio down.
Yeah, I was just trying to reach for the controls. All right.
And warning, if you guys sometimes get nauseous from like watching videos, or maybe you know from roller coasters that you might be squeamish, this is gonna be a spin, so might want to look away now if that makes you squeamish.
I'm gonna show you what we do to get into a spin. And we're gonna slow it down. Hi, Mom. Hi, Dad. The world is gonna start spinning.
Catch peak traffic, Bay Raider 32, single, Navy 860.
We're gonna stall.
City southwest, transiting south to north 500 feet.
We've departed.
That's peak traffic.
Right. We're bouncing around a little bit. This is the incipient phase. Okay, now notice how everything's steadied out. That's steady state. Now see, if I try to do the wrong thing by trying to push out of it, it'll go faster. Yep. If I try to roll out of it, it'll go faster too. All right, now power idle on neutral. Kick forward. Boom, we're out.
So hopefully you can see there, you know, I've already mentioned I studied flight stabilization control for drones. Now this is a demonstration with a plane with people in it, and in terms of the application from, you know, this aircraft, they're training people that fly all types of aircraft. But in terms of, you know, the importance and kind of relating that back to my Capstone project, that's a cool demonstration from a stable but like, you know, upset flight pattern to a stable normal flight pattern. So I thought that was a very cool video, just showing what a spin recovery looks like. So in terms of other stuff I've done, and I'm relating this back to my Capstone project, I created a computer-aided design of an entire plane for vertical takeoff and landing capabilities. So in terms of using skills, I used Inventor to create the CAD you see on the right of the plane, creating wiring schematics. And specifically for this plane, there's 3 motors, what it can generally be called a tricopter configuration. But for this design, the two motors on the front can be tilted up and down to transition from being used for the up and down motion for vertical takeoff and landing to the two motors being tilted forward for the forward flight configuration. And so another thing, flight controller configuration and tuning, kind of my experience from how stable and how sometimes there can be an oscillatory system, how to tune a system even without having all the core understanding of the math that goes into that. So I was applying these skills from my classes that I took in high school. So I want to show a couple of videos from that just show off what the idea of the project was. So you can see here, front two motors, they'll tilt forward to an angle about 45 degrees. And then at the full forward motion, rear motor shuts off, front two motors are in the forward flight mode. And that was the goal behind it. In terms of practice, when I actually got to testing it, it did get very challenging because of how, I was really loud on that. When I got to testing the prototype, it was a lot heavier than I expected, from having to improve the structure to handle those loads. And also from my experience with the flight controller configuration, one of the difficult things that I'm still learning about, even as a senior, is the math that goes into a transition from a vertical takeoff to forward flight. But this is just a demonstration of that technology in terms of the control using three motors. When you have three motors, you have an unstable system because the torque is not balanced. So you can somewhat see the motors being tilted by the servos in this video, hopefully. But that's just a cool, thing besides my Capstone project that I did while I was in college. And then one of the coolest things that I've gotten to work on by far at the University of Alabama has been working with UASpace on a CubeSat, which is a small satellite called Bama 1. And this is specifically going to be the first satellite from the University of Alabama to go to space, which I have it on the slide list here this month, but it's expected to launch this Saturday, actually. So I'm very excited about that. And this is testing a drag sail. So in terms of the technology, we're trying to just specifically test this while we're in low Earth orbit. And I've been an active lead in this from the proposal phase all the way to the final integration into the dispenser. And one of the cool things about that is I've gotten to design and test flight hardware and software. So I'm going to show some things off here. Hopefully you guys will try to learn something every day, and I'm hoping you guys might have not known this before. But in terms of why use a drag sail, a lot of people have been asking about our payload. So I want to start by saying satellites today are getting much smaller with the technology, and many companies want to launch constellations of CubeSats or small satellites to low Earth orbit. It's one of the fastest ways to get people connected, and it has the lowest latency in terms of the distance from the Earth. And at the end of life, a lot of these satellites are designed to, just come back to Earth, in around 5 years in terms of the mission design, if they stop working at low Earth orbit, at least. But in terms of if you wanted to remove your satellite from orbit and not have space junk sitting up there for an extended period of time, you can use a drag sail, which doesn't require active thruster propulsion. With a little bit of atmosphere that's up there at low Earth orbit, with a drag sail, you can change from taking 5 years to between around 50 days to 5 months, depending on how the sail deployment is in terms of if it's the full area or not that's exposed, and also just the space, the atmosphere in terms of the exact altitude and the space weather as well. But just trying to show off, this is what the sail looks like that's attached to our satellite. So in terms of the payload, it's actually pretty cool because the concepts should hopefully be familiar. We're using a stepper motor that is just like the same type you'd see in a 3D printer, aside from being vacuum rated because we're going to space. And you can see here it's connected to a screw that's pushing the payload up and down. So if you've seen a 3D printer before, if you haven't, I'd highly encourage you because 3D printing is awesome technology. But a lot of times they'll use stepper motor with a screw to push the nozzle up and down instead of using a belt system. So almost the exact same idea here with that used a deployer drag sail. And then you can see at the top here, when it gets out of the satellite, it's much easier to see that it's a clear mylar material. It's wound up with an origami pattern to make it stowed as tight as possible within the satellite. And then on top, there's actually tape springs that are wound up in a coil. And it's the same stuff you have in a tape measure in terms of the material. We weld them back to back, and they create a like an eye shape cross section, and that's actually very stable in terms of returning to its shape in case it's deformed. And now I'm going to show on the right here. Here's what the deployment looks like once the payload's out of the satellite. We burn a resistor, which essentially burns up a fishing line at the top, and you'll see it. This is in slow motion, obviously. You'll see it deploy the booms, which then drag the clear mylar out. So in terms of this, I think this is one of the coolest videos we've ever made, because you can actually see here not only deployment of sail, but the satellite's reaction in terms of the conservation of angular momentum. You can see the satellite spin in the opposite direction of the booms when it gets out. So I think that's an awesome video in terms of just practical testing and also applying, familiar concepts from 3D printing. So some other cool things I've gotten to do this last summer. I mentioned I'm an aerospace engineering student, but I did have an interest in electrical engineering as well. And I learned how to design, fabricate, and test printed circuit boards. So you can see here's 2 different ones I worked on. This was not the way it looked when I designed it the first time. It took me over 27 revisions just to get the one on the left to be the design you see there. So I want to emphasize that persistence and receiving constructive criticism is very valuable in terms of getting a good product. But in terms of the functions, this helps us driver stepper motor. There's a driver on the board for that. There's drivers for the attitude determination and control system. And there's also extra chips for communication with our electrical power system and other key functions of our satellite. So this is internal to the satellite, and on the right side you can see a smaller circuit board that's external, that's used for servicing the satellite in terms of changing the software, charging the satellite, and also turning on and off the electrical power system. So both of these designs I actually generated. So I have the awesome opportunity to say I helped design hardware that's going to go to space. So in terms of the project experience, obviously it's, I think, my most valuable. I've pivoted from working on drones to working on flying planes, and then pivoted now again to now working on satellites. So in terms of this specifically, I've learned a lot about refining a design for the space environment. So I mentioned previously, people probably know space is hard. You have to deal with a vacuum, extreme temperatures, both very hot and very cold temperatures, and just also the launch loads. We had to shake our satellites rigorously just to make sure things wouldn't fall apart. So that was a very valuable experience. In terms of communicating with vendors, we bought a lot of our parts commercially off the shelf, or COTS, COTS. You might hear that as you go into industry quite frequently, as people try to reduce their development times. You can just typically find someone that's designed something that works and integrate that into your system. But the third bullet going with that would be working with interface control documents, especially when you have your hardware interfacing with other stuff that you bought. It can be very challenging, especially if it's not all from the same vendor, to interface with things, and that's often where things fail. So in terms of just the experience with that, that's been a little bit challenging, but also very rewarding in terms of understanding the system as a whole. What it's like to recruit and motivate a great team, especially when you don't have experience. I mentioned it, but if I didn't say it clearly, we did this project in about 3.5 years, coming in as freshmen, really interested, but not really having the skills to build a satellite, and then working really hard to learn as much as we could in a short amount of time. And just keeping each other motivated. It was challenging, but also a very fun experience. Then I would say the value of trade studies and system models. No model is perfect, but in terms of like understanding how a subsystem or a system as a whole might respond electrically, or in terms of the communication system that you want to use, just trying to understand the options that you have and hopefully finding the best option at the time. That would be extremely valuable. And in our case, with us trying to go fast, it was the only real way to get things done in that quick a time. Then moving on, I got to actually work on the subsystem testing, and not only the payload, but of the design circuit boards, the printed circuit boards I mentioned previously, and also integrating all the parts of satellites together. I got to work on that. So you can see me on the right there holding the entire integrated CubeSat, which was extremely exciting. And then working with industry professionals. So aside from vendors, I've gotten to work a lot with NASA in coordinating our launch, and also talked with international organizations to coordinate our FCC license transmit. So just working with industry professionals in that sense, and also the people of Huntsville in terms of the great mentorship they have there as well on space systems. It's a great opportunity. So in terms of the future, where I will conclude today, I want to mention the exciting thing is we expect the Astra rocket that's carrying Bama 1 to hopefully launch as soon as this Saturday with our satellites. And going along with this, I've also recently received an offer to work as a mission manager at Astra in California. From them learning about my experience while I was delivering the satellite, they actually were very interested in bringing me into the team. And want to emphasize this, my last point, which is I'm still looking at full-time work for the summer, so I haven't taken that offer yet. But just in terms of scope, as I wrap up my senior year studying aerospace engineering, I will be hopefully going into work this summer. And with that, I hope you guys enjoy my presentation. I'd be happy to answer some questions.
All right.